Okay. Okay, so I'll be talking about the a review topic, exploring contemporary approaches to detecting micro and nanoplastic in ecosystem. So this is a brief um, introduction about myself. So my name is Christian Enyo. I'm currently doing my PhD at the Graduate School of Science and Technology Engineering, Saitama University, under the Green and Sustainable Technologies. I have been writing and publishing since 2016. I have written over 160 articles, book chapters, and I am listed among the top 500 authors or scientists in Nigeria by Scopus. I also have special interests in philosophy, psychology, and social sciences, and also interest in experimental computational artificial intelligence method techniques. So recently, I published a book, which is Sadness Unveiled, A Positive Perspective, and some of my current research interests is to use both experimental and computational methods to study plastic degradation by both chemical and biological methods and the use of artificial intelligence in environmental chemical research. So for this presentation, this will be the outline. I'll talk about the introduction, the aim and objective, the characterization method, and both the chemical method and both index method in studying micro or nanoplastic in environmental samples. So currently, we are facing an issue of a plastic waste problem, which is due to continuous industrialization. And the annual production of plastic continues to increase, and estimates put it that by 2100, we are going to have about 1.5 or more than 1.5 gigatons of plastic. And as we have the continuous production of this plastic, the waste that is being generated also increase, which it is estimated that about less than 1.5 gigatons of plastic waste will be generated annually. And most of this plastic that has been produced are from packaging, which most of the waste plastic we have in our environment are also from packaging. Also, the amount of plastic that are still in stock is still also very much, which is mainly from building construction. So generally, we are facing an issue of plastic waste problem, even though there are efforts on trying to recycle plastic waste. But the amount of plastic that is being recycled is still very, very less. So we have still have much plastic in our environment. And because of this continuous presence of plastic in the environment, we are facing an issue of microplastic, because this plastic, while they're in the environment, they tend to break down into smaller plastic, where they form micro or nanoplastic. So we have the microplastic, we have the mesoplastic, and we have the microplastic. So data suggests that about 82 to 578,000 tons of microplastic has been recorded in the environment. And this is equivalent to about 50 mil, that is 30 billion or 50 mil plastic bottle, which is very, very significant to have this amount of microplastic in our environment. Moreover, this microplastic can also still break down further into nanoplastic. And those ones, their sizes are less than 1 micrometer. So where are these microplastic from? So they are mainly from two sources, which is the primary source and secondary source. Primary source of microplastic include the clothing industry, the fishing, the shipping line, plastic production, and waste treatment plants. While secondary microplastic sources include where we have large plastic in the environment, which undergo fragmentation, maybe by mechanical friction or by UV or by other environmental factors. So these are the major two sources of microplastic and potentially nanoplastic in our environment. And microplastic are now ubiquitous in nature, whereby they have been reported in soil, air, in our food like salt, sugar, in marine environments, in drinking water and soft drinks. So they have been literally discovered in everywhere. So it is a global emerging problem. And because of the wide or the ubiquitous nature of this microplastic, we tend to consume them as humans. And in one of my recent review, I tried to review the amount of the presence of micro and nanoplastic in our bodily fluids. And from that review, I found out that microplastic has been reported in sputum, in hearts, in our blood, in our placenta, in the kidney, in the urine, in the testes, in the semen, and even in breast milk. So all bodily fluid system, we've recorded microplastic in all bodily fluid system. So they are a serious issue. And once they enter the body, they are being transported into the different bodily fluid through the blood. So this microplastic is a very big issue that we are facing globally. And some of the impacts of microplastic can be grouped into three, which include the particle toxicity, the biofilm associated, and chemical toxicity. So the particle toxicity involves whereby when we consume too much microplastic, or when an organism consumes too much microplastic, they tend to build up in the body, causing some negative effects. While the biofilm associated involve whereby this microplastic have a very good surface for microorganisms to form like a biofilm and like a cell, a cellular structure on the surface of this microplastic. And they use this cellular structure to transport pathogens and some viruses. And the chemical toxicity is included the chemical composition of this microplastic, because most of this microplastic contain additive. And why they are being ingested, they have the potential to leach these additives that are present in this microplastic, which is under the chemical toxicity of micro or nanoplastic. But the risk of microplastic depends on the human, the vulnerability of that human, the amount whereby we consume and the amount we release from our body. If the amount we consume is maybe less than the amount we emit from our body, then maybe the risk might be a bit lowered, because it has been suggested that about 90% of plastic we consume are being excreted from the body, which we can see maybe from the semen, from the feces, and from different part of the body. So generally, we should study microplastic because it is critical to limit the growing severity of microplastic pollution problem that's gone worse in recent years. And the examination of microplastic is extremely important for determining the traceability of microplastic and assessing how effective they are from the environment. So when we study microplastic, it is a crucial step for the basis of treatment of microplastic contamination. And now there are various methods available for analyzing microplastic. So in this study, in this review, I'll be talking about the different techniques or analytical approaches that we can use in the study of microplastic in different environmental matrix. So first, let's look at the analytical framework for microplastic analysis in environmental samples. So we can have samples, solid sample, which includes soil, sediment, food, or dust. We can have liquid samples, including water, sewage, and we can have air sample, including aerosol, sea sprays, and rainwater. So sampling. For liquid samples, we can use a grab sampling technique whereby we submerge the sampling bottle into the water and we collect our sample to the brim and we close it tightly using glass bottle. We can also use a Mantra Tronet. So using Mantra Tronet, we have to measure the particular area by which we are sampling, so that after using this straw to collect sample in that particular area, we can now report our results based on the area. Maybe if, for example, we cover like 2 meters or 2 meters, for example, and we recorded like 10 microplastic. So we can say 10 microplastic per 2 meters, for example. So for Mantra Tronet, we have to use we have to measure the particular area by which we are going to cover during sampling. And for soil, same is very similar. So we have to select a particular area, maybe on the beach side. In my previous study, I just make a W shape line. I collect 5 points or as many points as possible. So we must always ensure to collect representative sample I can describe the entire area. Another technique whereby we can use to collect sediment is they use the Van Veen gap. So this is submerged into the water, and we first of all unhook it. Then once the hook gets into the benthic or the bottom sediments, then we can now close it and we move it up. So this is another technique in which sediment samples can easily be collected. So for the analytical framework for water matrix, once sample is collected, we can filter the sample, then we digest the sample. After digestion, we filter, then we analyze. Sometimes we filter the sample to remove maybe very large particles, then we digest the sample to destroy maybe organic material, because organic material can be mistaken as a plastic or microplastic or nanoplastic. So we digest to destroy the organic matter, then we filter, then we identify. For soil, after collecting soil sample, we characterize the soil. I always recommend characterization because characterization can give us an information, a crucial information about the soil composition, and those soil composition could give information on could have a relationship with the composition of the microplastic in the soil. So we first of all characterize, then we homogenize, basic sample preparation. After we've done that, we determine the organic and inorganic composition of the soil. When analyzing soil sample or dust sample, it's very important to know the amount of organic matter in the soil, because the amount of organic matter in the soil will determine how long and what is the how long and what is the sorry, how long and what is how much digestion composition do we need to dissolve the organic matter in the soil. So after we finish doing that, we can do density separation. The density separation, we can use sodium chloride or sodium iodide for density separation, or zinc chloride. So the density separation, the density of the solution should be in a particular concentration whereby the microplastic can easily be floated on the surface of the sample. So we can easily separate. After density separation, you can analyze directly, because we already have microplastic floating on the surface of the sample, and this microplastic can now be collected on the filter, and then we analyze directly. But sometimes we might want to digest that sample again, then before we analyze. But if the particles are big enough, we can just manually sort them with our eyes if they are big enough. But there are some particles that are very tiny. If you have a microplastic about 1,000 micrometer, it is big enough for somebody to identify, to see. But very less microplastic, maybe like 1 or let me say 10 micrometer, they are very, very small. So we might need to use some advanced technique for visualization. So for air sample, this is the framework in my review study, which was published in Environmental Monitoring Assessment. So for air sample, we can have indoor air and outdoor air, the different compartments. For indoor, include the indoor air and the dust, that is deposited dust particles in the room. And for outdoor, we use rain sampler or particle fallout collector. These are example. So this is a rain sampler. So you just keep this device maybe outdoor or on the roof. Like in my lab here, in some samples we did on air sampling, we use this device. We kept it on the roof and we monitor for different days. We collect sample for different days. But for the indoor, you just need to use a vacuum cleaner to collect dust particles and analyze. So the first step is we pre-treat the sample by sieving. If we sieve, we can decide to sieve and move straight up to spectrometric identification. So depending on the type of sample or the dust sample, we can do density separation. When we density separate, we have to use digestion to destroy organic material before we now visual identification using the microscope. And when we use microscope for observation, we can say, okay, this is plastic or not. Then after we use microscope, then we can use a spectrometric or spectroscopic techniques to confirm that the sample or what type of plastic or what type of microplastic are in the samples. So similar step is also followed for outdoor sampling. So during the study of microplastic, we should consider quality assurance and control because microplastic, the experimental process could be undermined if a proper quality assurance and control was not considered during the experimentation. In my laboratory, if I'm working on microplastic, for example, I always keep a control sample, maybe just a distilled water in the same room as I'm working. And this sample is being analyzed similarly as I'm analyzing the microplastic. And then again, I have control for maybe the distilled water. When I'm using ultra pure water, I still analyze ultra pure water for potential microplastic. So the amount of microplastic I'm detecting in this, maybe in this ultra pure water or these blanks, I have to subtract it from the sample I'm analyzing because these are potential contamination. So sample collection, we must make sure we collect representative sample, replication, size, volume, number, and weather. We have to put this into consideration. When we transport to the lab, how we store our sample is very, very important. The filtration techniques, the subsample and the homogenization. We have to homogenize sample. If you're working in a particular space, we must collect representative sample. Representative sample can be collected maybe using a simple random sampling technique, or like in my case, I always draw like a particular shape on the field and I collect sample along the particular line. Then I can now homogenize this sample to have a simple sample. So there's a secondary contamination whereby non-plastic and clean equipment, we have to consider using non-plastic. Maybe you are collecting water sample and using plastic bottles to collect water sample. There's a high chance of contamination. The pre-filter solutions, we have to confirm because when you're preparing maybe like the zinc chloride or the sodium chloride or the sodium iodide for density separation, the liquid or the density, the sodium chloride itself might be contaminated by microplastic. So we have to put that into consideration. The laboratory space must be clean as much as possible, and we must always have blanks, field blank, lab blank, and background check on control. Very, very important. And if we are trying to optimize our process or validate our process, we must have a standard reference material, spikes. So we must have positive controls and negative controls. So these are very, very important for sample recovery. So you have a particular sample, and we introduce a particular amount of microplastic in this sample, and we try to analyze this amount of microplastic which we've introduced in this sample. So we can now estimate the sample recovery. If we introduce about 10 grams of microplastic and we are able to get like 8 grams out, so we can say that the recovery of this sample is about 80%. Then in our reporting of our results, blank correction, which I explained earlier, I talked about subtracting the amount of microplastic which you've recorded in your blank from the microplastic which you recorded in your sample. So if you have 10 microplastic in your sample and in your blank sample, you found that you got 2 microplastic. So the blank correction is that we subtract the 2 microplastic which we found in the blank sample from the sample which we've analyzed. Then we have to report the limits of detection, quantification, and potential particle contamination. So we can estimate this from the blank control. As an example, this is a study which is published in Earth in 2023. This is a sample I did on Gary sample. So I weigh a particular quantity of Gary sample, then I separate them, then I did density separation, then I have my laboratory control, then I decant, then I sort them visually, Then I quantify the type of microplastic using FTIR. So the technologies for microplastic analysis in the environment. So they are basically microscopy, thermal analysis involving heat, spectroscopic, and some emerging technology. For physical characterization, we can use a visual or imaging technique, which involve basically microscopy. So we can have the optical microscopy, a fluorescent microscope. This is a fluorescent microscope in my laboratory here in Japan, which we use in studying microplastic. And we can use a transmission electron microscopy and a scanning electron microscopy. So these are some studies. This is a study conducted by Lee in 2013. They used a fluorescent tagged P bead. So because PE microplastic have the ability to absorb energy, and during emission, they can actually produce coloration. And this has been used to monitor maybe some kind of effect of microplastic in organism. So, but some of these methods have a limitation. Like this study conducted by, published in the Biomed Central, it was difficult to differentiate between the nanoplastic, and particulate material in a sample. It was very difficult. But in this study by Lee, we can easily identify the microplastic, which has been tagged in the sample. Another technique is using the scanning probe microscopy, which is also under the microscopic technique. So the scanning probe microscopy is a kind of microscopy in which pictures of the surface are created by scanning the spectrum with a physical probe. So there are different probes that are being used in this technique. One of the most common ones, which has been used in many studies, is the atomic force microscopy, which has been mostly used in microplastic studies. And these different SPM techniques have different probes. They have advantages, and they also have disadvantages. So some of the drawbacks from this technique is that it gives little or no chemical information. It just gives you a picture of the surface. And it is sometimes difficult to identify the precise geometry, and it has a very high scanning rate. So some of the advantages, like the atomic force microscopy, which is commonly used in the study of microplastic, is that it is both, it produces excellent views of samples in both air and liquid media without the need of a vacuum chamber. So the atomic force microscopy is very, very efficient when compared to other scanning probe microscopic techniques. So this atomic force microscopy has been very, very muchly used in Nigeria, muchly used in microplastic study. And it is also available in Nigeria. There are some techniques which are used for determining the size, and which include the dynamic light scattering. These are some advanced tech which has been used to study microplastic. So if a nanoparticle suspension is exposed to a light beam during the dynamic light scattering, a process called scattering occurs, which causes the direction and intensity of the incoming light to alter when the particle impinges on the light beam. So based on the dispersion or the scattering of the incoming lights, we can estimate the amount of particle present in the sample. Again, this kind of technique will give information about, so you have this amount of particles, but sometimes it's difficult to identify what type of microplastic or what type of polymer is present in this sample. So these are some of the drawback of this technique. So because in a sample, sometimes microplastic are not settled, so they are always in continuous random motion due to their kinetic energy. So the changes in the intensity with time includes information about their random motion, and this is utilized to determine the particle diffusion coefficient. So the diffusion coefficient of this particle we use to estimate the amount of microplastic that are suspended in the solution. For chemical identification technique, we have the common electron microscopy, or some people call it maybe scanning electron microscopy, which is coupled with energy dispersive X-ray. So what this technique simply does is that the scanning electron that is the same will help us to identify the surface of this microplastic, And that particular point that is being pictured can be analyzed by EDX. So the EDX will give us the chemical composition of that particular surface. So based on this chemical composition, we compare this chemical composition with a reference sample polymer. And based on the closeness of this chemical composition with the reference sample, we can say that, okay, this is a polymer, a microplastic. And this microplastic is made up of PET or polystyrene. So that is how this technique works. And it has been used in many studies. There was a study we did in UNN on bottled water in southeastern Nigeria. We used the same EDS technique in our study. The study is published in Journal of Environmental Analytical Chemistry. Another techniques which is very common in the study of microplastic is the infrared and Raman spectroscopy. So the infrared spectroscopy uses an IR source. So this IR source is being beamed on the sample and they are being separated. We have the reference and we have our sample. So based on the reference sample, there's a readout, and this readout is being analyzed to determine the polymer type. For microplastic, we don't just use the FTIR. We have to attach a focal plane array reflectance or attenuated total reflectance, that's ATR. In my laboratory, we always use the ATR. This is available in my laboratory. So we use the ATR FCR spectrophotometer, which we use for analyzing very tiny microplastic particles. Similar to infrared, we have the Raman spectroscopy. So their principle is very, very similar. So these techniques are non-destructive. We have destructive techniques, for example, the light scattering technique. So some of those techniques destroy the microplastic sample. But this technique, after we analyze, we can still recover the microplastic sample which we've tested. So the Raman spec is a bit similar to the IR, because the Raman spectra which is being generated is interpreted similarly to how we interpret IR spectroscopy. This is an example in the study of Silva et al. In 2018. This is Raman, this is IR. This is the result obtained from Raman spec, this is the result obtained from IR. The output of their result is very, very similar. This is a particle 1, and this is a reference polyethylene. This is for IR. So the interpretation of this is very, very similar. So interpreting IR or Raman spec can be done in different ways. One of the ways whereby we interpret spectra for microplastic is using the OpenSpaCy. OpenSpaCy is an open source website developed by Win, I think Win Koga. And so on using this OpenSpaCy, you just need to upload your FTI or your Raman spec, and this will help you try to match it with available reference sample or spectra that has been uploaded in the library. And from there, we can identify, okay, this is a polymer, this is a polymer, or this is just sand, or this is just different kind of microplastic. And this will give you the correlation value, is 0.7, 0.9, and so on and so forth. Another way by which we can analyze our IR or our Raman spec is by identifying the characteristic peak. Study by Vera Signam in 2021 did a comprehensive review and identified specific peaks that represent the different polymer based on what people have been reporting. And this study from this paper, we can actually see, oh, this peak, this stretching peak equates this particular compound or this particular functional group. And based on that, we can know that, okay, this is a LDP or HDP or a polystyrene or polyvinyl chloride. Another technique which I mentioned before is this atomic force microscopy. The atomic force uses a cantilever, this cantilever, with a very sharp tip. That's a very sharp tip to scan over a surface. This is a surface. So this is cantilever. a sharp tool, they scan over this surface. So as they scan over this surface, they give us an image, and that image is recorded on this computer. This is a result from using atomic force microscopy. Atomic force give us the surface, and if we attach IR, that is the infrared spectroscopy, we can have atomic force microscopic infrared. So the particular spot, which is very similar to the same, cannot be analyzed by IR. And based on the spectra, we can identify the type of microplastic or the type of polymer which is available in that sample. So this is another technique which is very useful in the study of microplastic. These are some of the destructive technique. Pyrolysis, gas chromatography, mass spec. So we have GCMS, which is attached to a pyrolyzer. So when the pyrolyzer destroys the sample, they emit specific gas composition. And this gas composition, like the volatile fragment, is being collected into the GC, the gas chromatograph. The gas chromatograph will separate them, the gas that is coming from the pyrolyzer. After it separates them into different decomposition products, the mass spectra will now identify their individual fragments based on their charge to mass ratio. And based on this, we can identify the type of microplastic present in the sample. So this technique, we call it destructive technique. Once you are done with this technique, you can recover your microplastic sample, which you've obviously destroyed from the pyrolyzer. So another technique is a thermal desorption. So also similar, but in this case, we have a GC, which is attached to a mass spectrometer detector, and which is attached to an automated thermal desorption. So sample is collected onto an absorbent packed glass or stainless steel tube. The sample is concentrated on the absorbent. The packed tube is heated, which is the thermal part, and the compounds are released into the carrier gas desorption, where they are swept into the GC column. So GC will help us now take the sample and analyze. And the mass spectroscopy will give us the individual fragments, which is the charge to mass ratio. Because when the compound is breaking, as they are breaking, they are fragmenting. Each fragment has their own charge to mass ratio. And based on the charge to mass ratio, we can identify maybe the product being formed and how, based on the product being formed, maybe for example, we have the polyethylene, maybe the first fragment was ethylene, one part of the ethylene, and we have another fragment with another part. So based on those fragments, we can say, oh, this is actually polyethylene microplastic. These are some techniques, but we can also, okay, this is an example of some studies. This was a study done by, published in MDPI. So they coupled a thermal desorption GCMS and they combined it with a pyrolysis GCMS. So this is a tandem technique, TD with pyrolyzer. This study was done by Richard in 2020. So they coupled both TD GCMS and PY GCMS to analyze particle products. This is example from the study. We have a sample A, we have the sample B, and we have the sample C. So they use a pyrolyzer heated at 600 degrees, and from the output from the pyrolyzer, or we call it pyroxylates, the GC column will help us to separate them, and the mass spectra will help us to determine the charge to mass ratio. And in this study, they use a library search called F-search. So the F-search can be used, like in the case of the FTIR, we can have the open spaces, which we can use to interpret the FTIR spectra. But for this pyrolyzer technique or thermal techniques, there's an F-search system, which is being used to analyze different type of microplastic easily based on the results obtained from this technique. So the F-search was developed by the Frontier Laboratories Limited, which consists of a search software for and 4 unique libraries, which the users can select for the respective purposes. So this is an overview of the FSearch system. The FSearch includes a thermogram. This is a library for library, and a thermal desorption library. It contains a polymer pyrolysis GCMS library and a polymer pyrolysis library. So once you obtain results from your analysis from maybe the TD, GCMS, or the different techniques, you put into this FSearch system. The FSearch system will now, based on the spectrum or the spectra which has been uploaded in it, can now give us the structure. And from there, we can say, oh, this is a polymer, a polystyrene, or a PET microplastic. A PET microplastic. So based on this, we can identify the different microplastic in our sample. But recently, there have been some more easy method, which is a quantitative index method, which was recently developed by Lee et al. In 2022. So because microplastic or plastic or polymer are basically made up of 6 elements, which is carbon, hydrogen, oxygen, nitrogen, sulfur, and basically chlorine. Maybe like we have the polyvinyl chloride. So these guys, these authors, thought, okay, if we can differentiate between which we can separate between a particulate matter, organic matter, we can actually, from the total organic matter in a sample, if we have a sample of soil, for example, and we burn this sample, we have ash. Those ash content or the organic matter we have left incorporates both the microplastic and the particulate black carbon. So in their technique, they try to estimate the amount of microplastic, that is microplastic organic carbon, by separating the total organic carbon in the sample from the particulate black carbon. What did they do? They use potassium disulfide oxidation and Fenton digestion in sequence for the quantifying of the MMP. So you have sample, you filter sample, and you digest. Once you digest your sample, you have total organic matter in the sample. The total organic matter in the sample contains both organic matter for the microplastic and the particulate black carbon. Same sample is then analyzed in a different technique. And from this technique, we obtain only particulate black carbon. So the TOC organic carbon for the microplastic or nanoplastic that is in the sample is obtained by subtracting total organic carbon by the total particulate black carbon in sample. So it's a very easy method. So this study is available in Analytical Chemistry. It published in 2022. Very easy method, but you're going to use a lot of chemical. So it's a bit expensive technique. Okay, so this is just an addendum. In the study of microplastic also, we have to consider evaluating risk, because to reach a judgment or a conclusion about the existence of microplastic or nanoplastic in a specific matrix is very challenging and sometimes very difficult to interpret, because like when I was talking about collecting sample on the water, I said we have to report the microplastic particular area which we have sampled. And sometimes because of this, it's difficult to compare studies. Some people report a particle per meter square, some people report a particle per 200 meter, some particle per liter. So different reporting units for microplastic study. So one of the ways whereby we can easily compare the impacts of microplastic in a particular area, let's say for Lagos State and compare for Imo State, is whereby if we can have a metric system for comparison. So in this study, my study published in Environmental Science, we try to provide different analytical models index models, whereby it can be easier for us to compare between microplastic reported in different areas. So the summary of the index method is here. We have the contamination and accumulation and pollution load assessments of microplastic in different metrics, including water, soil, air, or food item, marine organisms, ecological systems. So we have the polymeric risk assessments. There is ecological risk assessment of microplastic. And we also have for the health risk assessments, which is the plastic estimated daily intake, the cancer risk assessment for microplastic. So most of these models has been applied in some study. Like in my study, which I did on Gari, I applied these models. And most studies are now adopting these techniques in analyzing or in comparing their data. In conclusion, this study reviewed technologies for quantifying and identifying microplastic in environmental samples. So generally, for microplastic particles less than 500 micrometer, spectroscopic techniques are important for their identification, while the quality of results obtained strongly rely on good sampling and effective sample purification. So during purification, aggressive agents, maybe strong acid and alkali solution, should be avoided to conserve the whole plastic spectrum, and because aggressive solution negatively affects certain plastic polymer. In my Gari sample, I used hydrogen peroxide. So because nobody has studied Gari previously, I was not sure about the amount of the strength or the strength of the hydrogen peroxide should I use for digestion and how long. So when I used the wrong one, by the time I could go back the next day, everything was black. So we have to be careful about using a strong acidic or alkaline solution. An ordinary visual inspection of sample alone is insufficient. So, but when in tandem with optical microscopy, it becomes effective, especially in the case of particles less than 500 micrometer. So visual spectroscopy is not enough. We can be looking at an organic matter and we think it's a polymer, and we can count it as polymer. So pyrolysis, GCMS, and TG is based on combustion techniques, works for a larger particle. So this technique is very efficient for large particles. So SEM, EDS, and atomic force microscopic infrared techniques is better updates to optical spectroscopy by providing information on the degradation process of plastic particles and provide both elemental and chemical characteristics. Micro Raman is very effective for particles less than 1 and greater than 10 micrometer respectively. Raman spectroscopy less than 1 micrometer and FCR greater than 10 micrometer. Spectroscopy techniques can create an added value as they also provide information on polymer composition. So some of these techniques are cost effective. Some of them are time consuming because of the time for preparation. And so generally on the study of microplastic, techniques have been both destructive and non-destructive method, and sometimes often a combination of two methods, one separating and the other one quantifying. So my final note is that to make the evaluation of pollution and risk assessment easier, environmental analysis needs quick, ineffective procedure that can handle a lot of samples, because studying microplastic is very difficult. It is very difficult. Counting and taking your time to do things is very, very difficult. So this underlines the necessity for methods that have been refined and are designed to swiftly provide the necessary information on each sample, unless an academic interest justifies a thorough and consequently time-consuming less. So, however, it is essential to pick and combine methods that offer the bare minimum of information needed to respond to the analytical query. So, for further reading, these are some studies which provide more information on the technique for microplastic. And thank you for your audience.
Wow. Thank you, Enyo. Thank you for the beautiful presentation. Thank you for your time. This is really very beautiful. So now I open the floor to the lead reviewer, Dr. Fatoussi. Please, you have the floor now. Thank you. Hello, Dr. Fatuse. Kindly unmute.
Hello, good morning. Hello, good morning, everybody. Can you hear me?
Yes.
Hello, good morning, everybody. Can you hear me? Well
Good
done,
morning.
Dr. Enyo. You did give a very beautiful presentation. Gave a very beautiful presentation. Well done. You mentioned a lot of things, and your write-up, your journal, your article was well written. Well done. Thank you. And I checked your profile. You've done a lot of work, and then you mentioned that this method you reviewed can be used for analyzing or checking both nanoparticles and nanoplastic and microplastic. May I ask which of them is more toxic, microplastic or a nanoplastic? Which one is more toxic?
Okay.
Hello?
I can hear you, Doc. Thank you for your question. So if I'm going to think about the more toxic between microplastic and nanoplastic, so for now it's difficult to, maybe there are not enough study yet to tell us which one is more toxic. But from my own understanding, I feel that nanoplastic should be more toxic, because nanoplastic, because of its size, I believe it can actually reach more parts of the human body. Like currently we have, yeah.
Thank you very much. Well, in your paper, you suggested that nanoplastics are mostly from cleaning and calibration, and then further definition of microplastics. I was thinking that nanoplastics too may also be from leaching. When you leach plastic materials, there are many things that are made of plastic. So when they think that also leach nanoplastics, right? I'm just thinking. Hello?
Doc, maybe I could not hear you very well. You said that.
So I was just looking at the sources of nanoparticles from the paper
sources.
we are reading.
Yes.
So you said the cells are from cleaning material, calibration of nanoparticles, and further degradation of microplastics. That was the source in your paper.
Yes, I said so.
So I'm saying, but I'm thinking that is true. But in addition, nanoplastics, I'm just thinking, you're there. I'm just thinking that maybe we could also say from leaching of plastic materials generally.
Yes.
Some plastic might just go straight to nanoparticles. So every time we use plastic materials, there's a risk of also taking a nanoplastic. I'm just thinking,
yes.
Then of all the pre-concentration methods mentioned, so solvent extraction, solvent evaporation, membrane filtration, ultrafiltration, ultracentrifugation. Which will you think is the least expensive, and which do you think is the most efficient? Your write-up you seem to favor ultrafiltration from the way you celebrated all of them from your paper.
So from that paper was in 2021. I think most efficient can be a bit relative, because different laboratory could have which one is more efficient. So to have more efficient or most easiest to do for me, or from my point of view, is to extract and use microscopy then FTIR. But
you talked
FTIR
about the concentration method. You do a job, sample collection, digestion, pre-concentration, separation, and analysis.
Yes. Is it you're talking about the pre-treatment method? Okay.
Yes. Which one? Pre-concentration. Which one will you?
Pre-concentration.
do you think is most efficient? Which one is cheapest? Because in our time now, if we have grants, we want to go for the cheapest one.
Yeah,
At
cheap
least.
one.
Yeah,
I
but
think
as efficient.
to determine which one is more cheap, we have to first of all consider the chemicals involved. I'm trying to like look through the paper.
If
We
your
have to
paper on
consider
process, that's the paper we're
processes. Yes.
paper on process, that's the paper we're reviewing.
So we have for the sample preparation, we have pre-concentrate, we have the membrane filtration, ultrafiltration, ultracentrifugation, solvent extraction. From my own experience working in this lab, I can say maybe the membrane filtration is very cheap because we use membrane filter and we use a vacuum pump to force the filtration to move faster. So, and if we can do like a cost benefit analysis, that is more cheap from my own experience in this laboratory.
But in terms of efficiency,
For efficiency, from literature, there have not been a comparison of the different techniques. So most studies have used different extraction, yes,
there's room for research.
yes.
Various methods of pre-concentration, that's solvent extraction, membrane filtration, ultrafiltration, ultracentrifugation, to see which one was the best. Just for pH, example, pH and others, we've done such comparative studies. I think this is another research gap that to compare which is more efficient. And it will also be good to compare the separation technique, the HPLC electrophoresis, the hydro water. It will be good to do an experiment instead to compare the various techniques currently available, see which is the most efficient and how to optimize each of them comparatively to each other, further optimize them and find out which of them will give better results.
Yes.
I think that's a research gap that we are seeing of reviewing your work.
Yes. So what to do? No, I said, well, to do this kind of research in Nigeria will be very, very difficult because of some of those instruments.
For you that you have access, and maybe any one of us considering a postdoc.
Yes. So because it's very difficult, expensive. Even some of the instruments, very expensive to purchase. Okay, Doc, I'm listening.
Dr. Fatuse, we can't hear you again. Okay. Hello, Dr. Fatuse. Okay, before Dr. Fatuse comes up again, please, I want to know at what point can we differentiate between in the methodology for the microplastic and the nanoplastic? At what point can we now note the separation between when you want to analyze for microplastic and when you want to analyze for nanoplastic in the methodology?
Like some of the method cannot be used for nanoplastic. We can use, yes, because we have what we call we have FTIR micro spectroscopy, micro FTIR, sorry, and we have nano FTIR. So they are like an additional device, let me say device that is being attached to the FTIR just to be able to analyze smaller particle. So the ones for micro cannot be used for nano. Like Raman spectroscopy can analyze particles that are less than 1 micrometer, going down about 100, less than 1. Hello?
Hello, do you know I've been talking? I didn't know that nobody was listening. I've been talking and I didn't know nobody was listening to me.
We couldn't hear you.
Yeah, yes. Internet help me out. But I'm
Well,
back.
he's trying to explain a question that I asked.
Okay,
Then-
sorry.
Okay, so I was saying that the instruments by which we can analyze nano and micro, maybe like for Raman spectroscopy, we can actually use Raman spectroscopy for nanoparticle. I have not done it before, but because my Raman spectroscopy rather, has been shown to analyze less than 1 micrometer. So that range downward can maybe get to nano range. Then for FTIR, we have nano FTIR, we have micro FTIR. For the micro FTIR, we just attach an additional instrument like the ATR, attenuated total reflectance, or FPA based, we attach. For nano, I believe we also attach something, a device to the FTIR to be able to analyze nanoparticles. So because of their size, and it's very difficult to control. I don't know whether I answered your question, Doc.
Yes, yes. Thank you. So Dr. Fatusi, you can continue.
So I said that based on the paper, that you did an excellent job, and I've checked your profile, you're doing a great job, which I'm still, whereas microplastic for me is an area I've just recently got into and it's interesting. So we hope that after today, we can still write you, ask questions, and interact with you even on this. But like I said, there's a research gap that if you have funding close, it will be good. It's be a well-cited paper, a methodology to compare the currently available techniques, techniques of pre-concentration, techniques of, I've seen a paper on digestion, comparing digestion. I think it's your paper or somebody's paper, to compare digestion techniques. So it will be good to compare the concentration technique and the separation technique. So you compare the best, they'll use it to do separation techniques, compare, and see which result is better or more ideal result. Will be good for literature search. So that's what I found out while reviewing your work. I found a research gap, which if somebody has access to funding or somebody has access to a postdoc, should try and close that research gap. And I think you've done well and you're doing well. I'm wishing you all the best in your research. And well done. Thank you, Author Aid, for this opportunity of being a reviewer. Thank you very much.
Thank you very much, Dr. Fatusi. So the floor is also open for others to ask questions. If they want to ask questions, they can raise their electronic hands then, or you chat it up in the chat box, which will be read out. Thank you. Dr. Fatusi, continue. Hello? Do we have anybody that wants to ask question? Okay. So in the absence of none, we want to thank everyone for joining. But before we round up, we'd like to have picture. If we can turn up, yeah. So I don't know if Dr. Kojo, please, can you help us take picture from your hand? So we'll have to on
That's okay.
Our camera. Dr. Kojo, please, can you help us out with this?
That's okay.
All right, thank you. So let's on our camera for us to. Okay.
My phone, can you turn on your camera? Dr. Fumilayo, your camera is off. Gustav, iPhone, Leah. Gustav, Leah, Dr. Doherty, we are waiting for you. Okay. Okay, the first one is done. The next one.
Can you capture everyone at once?
It's I have to do it too because we are a large number.
Okay.
Lawa, your camera is off. Are you Dr. Ravi? Oni, Aishat, Dr. Ozu, Dr. Ami, your cameras are off. Here we go. The last one, and then we can leave. And the first group again. Okay. Last
Are you
one
done?
for the second group. Please wait, Jiffy, few seconds. Okay, the next group. Dr.
Okay.
Michael, your camera is still off. Okay, so I think we are done. Thank you.
Thank you very much, everyone, for joining this February edition.
Thank you.
And hope to see you in March. Thank you. And if you're interested in also presenting, you can as well reach out to me. I'll be glad to have you. Thank you very much.
Thank you.
Thank you for
Dr.
joining me.
Thank you, ma'am.
Thank you.
Thank you
Arigato.
for the presentation.
Thank you so
And we
much.
promise to get you the recordings. We'll get you a
Thank
link
you.
to the recordings on our platform. Thank you.
Okay,
Bye,
okay.
everyone.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Bye. Thank you.
Dr. Ayo.
Thank you,
Bye.
ma'am.
Thank you.
Bye, ma'am.
Thank you, ma'am. Bye.
Well
Thank you so
done,
much.
Dr. Ayo. Bye, everyone.
Thank you, Dr. Jagby. Thank you.
Bye.